So, welcome my friends, welcome to my next lecture. So, in this lecture I will talk about what is called gradient vector field. That means I already started this kind of notions in my last lecture. So, I will talk about the notions of gradient vector field, and then I will give couple of examples, and then later I will talk about what is called divergence, curl, and of course Laplacian. So, that is coming to 2 lectures. I hope I will be able to complete the concept of divergence, curl, and Laplacians. So, in my last lecture I talked about, in fact I started with, at the very end I discussed what is called gradient vector field. I will repeat, maybe I will start with once again what is gradient vector field, and then I will give some examples, and then you will see there are some connections with what is called gradient vector field, conservative vector field, or path independence vector field. That kind of things I think I will discuss today's lecture. Okay, so as I said, I think I should recall the definitions of gradient vector field. So, this is the one I already discussed in my last lecture, what is gradient vector field. Now, what is gradient vector field? You have to start with a vector field. So, that means let f be a functions some domain D subset of Rn to Rn. Suppose you have a vector field, I will say that that vector field is a gradient vector field if I have a scalar field f. That means if I have a functions from D subset of Rn to R, this is a scalar field. That means for each domain, each point in the domain, I am associating a scalar. So, that means if starting, suppose I have a what is called vector field given capital F, if there exists a scalar field f on this domain D such that I can write my capital F like as the gradient of f. So, that means start with a what is called vector field from some subset domain D subset of Rn to Rn. If I have a scalar field small f such that grad of f is exactly equal to capital F, then I will say that capital F is a gradient vector field, or in other words capital F of x is exactly equal to gradient of f at x, and it should be true for each x in D. And I already told you that if I have a scalar field f, then if I take the gradient it will becomes a vector field. So, therefore, gradient vector field is a special kind of vector field. That means a vector field capital F is called a gradient vector field if there exists a scalar field f such that if I take the gradient of this small f, I will get back my what is called vector field capital F. In such a case, that scalar field I will say that sometimes scalar potential. Okay. So, one example, very simple examples, if I have this vector field capital f x y is equal to y I cap plus x j cap, that means I am flipping x y to y x, it is a gradient vector field. Why? Because if I have these functions f, what is my functions f? It is a functions from R2 to R, right, and x comma y goes to x times y. Okay. So, now I am saying that this capital F is nothing but this one. Now, what is gradient of f? You can easily calculate. Suppose gradient of f at the point say x comma y, what is this? This is del f del x at the point x comma y, comma del f del y at the point x comma y, right. Now, you have the f is given. So, what is del f del x? That means y. What is del f del y? That means x, and which is nothing but my capital F acting on x comma y. So, therefore, capital F is exactly equal to gradient of f, and therefore, my vector field capital F is a what is called gradient vector field. So, these results I also discussed. I am saying that if I have, suppose you have a vector field capital F, and suppose you have 2 scalar potential which will give the same vector field. That means, capital F is equal to gradient of f1, and capital F is which is same as if I have another scalar potential f2 such that grad of f2 is equal to that capital F itself. If that is the case, then the result saying that the scalar potential f1 f2 they differ by constant. That means, f1 minus f2 should be some constant. This is constant. So, that is exactly I have written any 2 scalar potential of the same vector field. That means, take 2 different scalar potential, take the gradient, and it will give the same vector field. If that is the case, then the corresponding scalar potential must differ by a what is called constant. Now, this is another example. If I have this vector field, then this time I am having a vector field a capital F from R2 to R3. Okay. So, therefore, it says that okay. So, okay, I think it is there is a typo. Okay. So, this is not the case. So, this should be actually capital F of x comma y comma z, and this is actually f of x comma y comma z. So, therefore, capital F is a map from R3 to R3. So, that means I need a vector field from some subset d of Rn to Rn, like here I am in 3 dimensions. That means I have domain, here is the domain is full R3. So therefore this is my capital F, R3 to R3, how it maps x comma y comma z maps to x y 0, the same. That means x comma y comma z is the same. So that means this is the corresponding functions. So f of x comma y comma z maps to x comma y comma z. So this is the gradient vector field. Why? Because if I consider this scalar field small f, what is my small f? Small f is a map from R3 to R, small of x comma y comma z, which is nothing but half of x square plus y square plus z square. Okay. If that is the case, then this is true. Capital F is equal to gradient of small f. Why? You just calculate it. Gradient of f at the point x comma y comma z. What is that? That means del f del x at the point x comma y comma z, comma del f del y at the point x comma y comma z, comma del f del z at the point x comma y comma z. Just calculate it. Very simple. F of x y z is equal to half of x square plus y square plus z square. So what is the del f del x? Y z is constant. So that means it should be 2x, x square derivative you have to take, and 2 get cancelled. So that means this should be x. So when del f del y, this is y, and that is z, and that is exactly equal to f of x comma y comma z. Okay. So therefore this is another example where my vector field capital F is a gradient vector field. Now later on you will see this vector field is a special type of vector field which is like gradient of some scalar field, and since it is a special kind of vector field, the more nice properties it will share. Okay, that we will see. Okay, couple of example, physical example. So the temperature of a metal rod is heated at one end and cooled on another end is described by the corresponding, I think I have discussed capital T of x comma y comma z. The flow of a heat is described by the vector field. Temperature, that means the kind of value that can be described by the scalar field capital T, and when I will talk about the flow of heat, that means I am actually talking about the vector field. Okay. The energy and heat flux of a vector field is given by gradient of the scalar field capital T with some constant you have to multiply, that is minus of kappa, where kappa is positive, some constant. So that means this is a gradient vector field actually. Now this is one example where I have an example vector field which is not a gradient vector field. So I have discussed couple of examples which are gradient vector field. That means given a vector field, I can say that this is the corresponding scalar potential, and if I take the grad of that scalar potential, I will have that vector field that I started with. So this is the example where I have a vector field which is not a what is called gradient vector field. So what is that? This is actually this kind of vector field, you know, capital F of x y is equal to minus y I cap plus rotational vector field. Okay, it is not a gradient vector field. Why? Assume that it is a gradient vector field. That means suppose there exists a scalar potentials f such that capital F is equal to grad of f. So that means what? That means this will implies capital F of x y, which is nothing but minus y comma x, which is same as del f del x at the point x y comma del f del y at the point x y, right? So that's exactly I have written. Suppose it is a gradient vector field, that means there exists a scalar potential such that gradient of f, gradient of small f is equal to capital F. So that means this equality implies that your f of x is equal to minus y and f of y is equal to x. Now if I consider the second order partial derivative of this f x f y, that means f of x y will give you minus 1 and f of y x will give you 1, because what is f of f x is equal to minus y. Now if I take the derivative with respect to y itself, that means if I take f of x comma y, right. So that means first I am performing the derivative with respect to x and then y. So that means it will give you minus 1, and what is f of y x, that will give you 1, and this is not the same. Then why it will contradict? Now you see in my slides I said that unless otherwise specified, I am assuming that my vector field capital F is a C1 vector field, right. Now if I have the vector field capital F is C1 vector field, and suppose f is equal to gradient of f. Now since f is a capital F is a C1 vector field, that means my corresponding fx and fy, this should be what? C1, that means this should be differentiable and derivative should be continuous, right. Now since capital F is in C1, that means my fx and fy, this should be what? This should be differentiable and derivative should be continuous. That means differentiable means what? That means mixed derivative exists. That means fxx, fxy, fyy and fyx. These are the derivative, that is the derivative of fx and derivative of fy, right. So that means since capital F is C1, that means fx, fy, this is one more differentiable and derivative is continuous. That means all second order partial derivatives of small f should exist and they are continuous. Now, once they are continuous, that means the corresponding mixed partial derivatives they should be same. That means in that case f of x y should be exactly equal to f of y x at any point, right, since the second order partial derivative exists and they are continuous. So, therefore, if this is the case, but here it is not the case, you have f of x y is equal to -1 and f of y is equal to 1, these are different. So, therefore, thus capital F is not a C1 vector field, which is a contradiction. Okay. So, therefore, if I have this vector field capital F, which is a rotational vector field, it is a C1 vector field. Now, this C1 vector field, that means rotational vector field, it is not gradient vector field, because if it is a gradient vector field, that means if I assume that capital F is exactly equal to gradient of small f for some scalar potential small f, then this will implies that your f x is exactly equal to -y and f of y is exactly equal to x. Now, since capital F is in C1, that means the corresponding first order partial derivative small f suffix x and small f suffix y, these are actually differentiable and they are continuous. That means all the second order partial derivative of small f exist and they are continuous, means mixed derivatives, their value should be equal, right. We have already observed this kind of phenomenon in my earlier lectures. So, that means del 2f del f del x del y or del t f del y del x, both of them exist. Since they are continuous, their value at the point x y should be same, but this is not the case in this example, because here f suffix x y is equal to -1 and f suffix y x is equal to +1. So, therefore, this vector field capital F, it is not a gradient vector field. Okay. So, these are examples. So, couple of examples I have given where my vector field is a gradient vector field and this is a vector field capital F. In fact, this is a rotational vector field which is not a gradient vector field. Okay, as I said, so since I am dealing with a very special kind of vector field like gradient vector field, it will have some nice properties or it should share some nice properties. So, when a vector field is a gradient vector field, so this kind of note I have already discussed. Unless otherwise noted, I always assume my vector field capital F, which is continuously differentiable or it is actually C1. So, I will always assume that my vector field capital F, it is a C1 vector field, that means it is differentiable and derivative is continuous. Okay. That is the map capital F, which is a map from D subset of Rn to Rn. Now, what is this? This is called conservative field theorem. So, when I will say that my given a vector field capital F is a gradient vector field. So, this is a theorem, this is if and only if. It says that the vector field capital F is a gradient vector field if and only if capital F is a conservative field in D. And what is conservative field in D? I already explained, because if I have a vector field F from some domain D subset of Rn to Rn, I will say that what is called that field is conservative vector field if I take any two what is called smooth piecewise smooth curve with the same initial point, same final point, then the corresponding vector line integral of capital F over C1 is exactly equal to vector line integral of capital F over C2. So, that is called conservative. If I go back, I think I have written it. Okay, let me see. I think if you forget, yeah, you see conservative, right? Independence of path. Oh, sorry, same thing. Well, so I just missed one point. So, I say that a vector field is conservative vector field. That means if I take every piecewise smooth oriented closed curve C and D, C in my domain D, that means the vector line integral should be 0. That is called conservative. And earlier one that I talked about, that is actually path independence. Okay. So, that means what is conservative vector field? I already discussed. So, if I have a vector field capital F from some domain D subset of Rn to Rn, I will say that that vector field is a conservative vector field if I take any piecewise smooth oriented closed curve C inside my domain D, then the corresponding vector line integral of F over this contour C is 0. That is called conservative. And then what I am saying is that when my what is called vector field becomes a gradient vector field, this is the theorem. It says that if capital F is a conservative vector field, then it is a gradient vector field, or if F is a gradient vector field, it will be a conservative vector field. So, therefore, as I said, in view of the above theorem, we use the phrases like conservative vector field and gradient vector field interchangeably, okay, because both are equivalent. If it is a gradient vector field, then it is conservative, and if it is conservative, then it is gradient vector field. So, I will just interchangeably say that, okay, depending on the situation, whether it is conservative or whether it is gradient vector field. Okay. Then what? So, in the next slides, we will show that the above two concepts imply path independence of vector line integrals. Okay. As I said, so there is a connection between path independence and the conservative vector field, right? If you remember in my last lecture, I said And since I am now dealing with a very special type of vector field, which is nothing but the gradient vector field, and since it is very special, so it shares some nice properties. So that means of course I already see that if it is a gradient vector field, always conservative. So now later on you will see that in my next slide that it is also meaning that if I have a gradient vector field, it is conservative, also it is actually path independence. Let me see. Okay. So that is what so before that I have to say that what is path independence, I already said. So path independence vector line integrals. Okay. So look at this statement, either f is a gradient vector field in D if and only if f is conservative, if and only if f has independence of path in D. So I think in my last lecture I said that conservative and path independence both are equivalent. Now once I have a gradient vector field, all three things are equivalent. Okay. Before that, there is a theorem I have stated. What is that? If I have a gradient vector, like it is actually like, if you see, you can consider with that what is called fundamental theorem of integral calculus that you know. That means if I have a nice functions and if I integrate that functions a prime from a to b, that it will be like fb minus fa, right, if you remember. So that kind of things, a to b f prime x dx, which is nothing but fb minus fa. In real analysis you know. So sometimes this is called fundamental theorem if I have a nice functions. So similar kind of theorems is also happening here. So if I have a, let capital F be a gradient vector field. So gradient vector field means what? There will be a scalar potential with a scalar potential small g, and what I am doing is that let p and q be 2 points in my domain. So in my domain I am taking 2 points p and q, and what I am doing, C is piecewise smooth oriented curve in D, which starting point say p and end point is q. Okay. Then the vector line integral of capital F over C is same as like you have the integrations from the point p to q, and which is nothing but gq minus gp. So this is a notation. So actually one should be little careful that whenever I am writing a to b, that means there is a ordering a to b, right. But whenever I am writing p to q, that is to understand it, right. But there is no such kind of ordering between the 2 points p and q in R2 or Rn. Okay, this is a notation. So this notation means actually I am talking about the vector line integral of my capital F over the curve C, whose starting point is p, end point is q, and which is nothing but value of g at q minus value of g at p, like your fundamental theorem. Okay. So that means if I have the function, suppose this is my R2 and this is my domain D, and so suppose I have a point p and I have a point q. So suppose this is my curve C. Okay. So if C is piecewise smooth curve in D from the point p to the point q. Okay. Once I have this curve C, then integration C f dr, that means the vector line integral of capital F over C, which is nothing but, since it is gradient vector field, that means it is grad of g. So it says that g of q minus g of p. Okay. So that means if my vector field is a gradient vector field, then you can calculate the vector line integral of capital F over any contour C in the domain with starting point P and ending point Q is exactly equal to, you have the scalar potential because you will have a gradient vector field, that means the corresponding scalar potential is G, that means it is nothing but the value of G at Q minus value of G at P, like the fundamental theorem in the integral calculus in your single variable case. Okay. And this is a notation actually I am writing. So therefore this is a very nice observation, or I should say theorem. So that means what? That means gradient vector field is very nice vector field. So it says that if F is a gradient vector field, if and only if it is a conservative vector field, if and only if F has independence of path in my domain D. So that means, so whether I am talking about path independence, whether I am talking about conservative vector field, or whether I am talking about gradient vector field, everything becomes same. And not only that, I can have the calculate the vector line integral of my gradient vector field capital F over any curve C with starting point P and end point Q by scalar potential, value of the scalar potential, that means GQ minus GP. Okay. So of course, I should say that I have not I have defined the what is the kind of line integral. I think in my initial lectures I have defined. Anyway, in my forthcoming lectures, I will talk about more on what is called vector line integral, this kind of things, or line integral. So when I will talk about that concept of vector line integral, then it will be more clear what is the meaning. Of course, I already discussed what is the meaning, but I will talk about more on that. Then it will be more clear what is it. But this is actually the fundamental theorem of integral calculus in this. You can interpret in this way. Okay, but provided you have to look at the hypothesis, that means the vector field you have to deal with, that has to be a gradient vector field. Okay, so then only this kind of phenomenon is true. That means integration C f dr, which is gq minus gp, where small g is nothing but the scalar potential of the corresponding vector field capital F. And once I have a gradient vector field, then three concepts are equivalent. That means gradient vector field, conservative vector field, and path independence. Okay, two examples I have calculated, like as I said. So, you can calculate the vector line integral if I have a gradient vector field in terms of the values of the scalar potential. So, this is the one. So, suppose this vector field we have already seen, this is actually a what is called gradient vector field. So, what is the scalar potential? If you remember, scalar potential is f of r2 to r, f of xy is equal to x times y, right? Yeah, product. So, then your capital F, which is gradient of f, that means its first observation is that it is a gradient vector field. And suppose C is any arbitrary smooth curve from the point 0 0 to minus 1 comma 2. So, that means you have a point 0 0 and you have a point minus 1 comma 2, that means this is minus 1, okay, and this is 2. So, this is the point. So, that means this is my curve. Okay. Then just my earlier theorem says that if I have a gradient vector field, okay, and if I take any 2 point in my domain D, and if I take a curve C, smooth curve, piecewise smooth oriented curve in D from the point P to Q, then the corresponding vector line integral is nothing but the values I can write in terms of values of the scalar potential for GQ minus GP. So, that exactly that I have done the same. So, integration C f dr, so which is nothing but integration C gradient of xy, or that means this is my grad of f. And what is this? This is nothing but the scalar potential, that means xy from the point 0 0 to minus 1 comma 2, and which is nothing but minus 2. Okay. So, this is just applications of earlier theorem, you can have this example. Okay. So, that is fine. Another example, again we have already seen that this is also a what is called gradient vector field, and what is capital F? This is grad of small f, this is small f is the scalar potential, and if you remember small f of x y z, which is half of x square plus y square plus z square, right, that was there actually. Now, if I take any smooth oriented closed curve in R3, okay, so it has to be 0, right? Why? Because it is a gradient vector field, and what is the earlier theorem says? Earlier theorem says that gradient vector field, which is same as conservative vector field, and conservative vector field means what? If I take any piecewise smooth oriented closed curve inside my domain D, then the vector line integral of capital F over C is 0. So, therefore, vector line integral of capital F over C, which is nothing but this one, and this is exactly. If you calculate it, this vector line integral, you will can get it. This is actually 0. In fact, when I will talk about the definition of vector line integral once again, then you will see that if you calculated this object, then you will be able to see that this integral is actually 0, value is actually 0. Okay. So, these very two simple examples. Okay. So, now I will talk about what is called some necessary conditions of conservativeness. That means, if I have a conservative vector field, then it will tell you something, that is called the necessary conditions. And what is that? I have written as a theorem. So, what is the necessary conditions for conservativeness in Rn? Okay, what is that? So, if F is a conservative vector field in D, then what it says is that, so now you have a conservative vector field, that means you have a vector field capital F, it will have n components f1, f2, fn. So, I can write it. So, suppose capital F, this is the corresponding conservative vector field. Since it is a map from some domain D subset of Rn to Rn, it will have n components f1, f2 up to fn, right. This is the component functions. Then I am saying that if capital F is a conservative vector field, then if I consider the component functions say fi and fj, then the partial derivative of fi with respect to xj variable at the point x, which is same as partial derivative of fj with respect to xi variable. So, this kind of things will be true, and this is true for all x and for all ij with I not equal to j. So, that means I have a conservative vector field capital F. Suppose it will have n many components f1, f2 up to fn. What you do for I not equal to j, take two component functions small fi and small fj. Then necessary condition says that if I take the partial derivatives of fi with respect to xj variable at the point x, which will be same as partial derivative of my component function fj with respect to xi variable. So, whenever I am considering fi, I am talking about the partial derivative with respect to xj variable, and when I am considering component function fj, then I am talking about the partial derivative with respect to xi variable, and this should be true for each I and j with I not equal to j, where Fi is the ith component functions of capital F. So, this is a necessary conditions for the conservative vector field. So, if my vector field capital F is a conservative vector field, then this is true. Well, you know that conservative vector field, then gradient vector field or path independence all are equivalent. So, that means if I have a gradient vector field, then also this is true. So, okay, I have given a very small proof. Okay. So, what is given? F is a conservative vector field. Now, I just already discussed that if I have a conservative vector field, it is if and only if it is a gradient vector field. So, that exactly I have written F is equal to grad of g for some scalar potential g in D, because conservative vector field implies it is a gradient vector field. So, this is the first observation. Now, once I have that, now what is capital F? Your capital F, which is nothing but f1, f2, fn, which is same as gradient of g, and that I can write it as what? So, you can write it as, so like say del g del x1, del g del x2 up to del g del xn. This is the components. So, that means what is my Fi? So, my Fi you can say this is del g del xi for 1 lesser equal to I lesser equal to, right. This is the one. So, this is a gradient vector field, because a capital F is exactly equal to grad of g. Okay. Now, look, as I said, I unless another is specified, I always assume that I am dealing with a vector field which is C1 vector field. Now, if I assume capital F is in C1, that means I am talking about g is in C2. Now, capital F is in C1 and capital F is exactly equal to this. Now, capital F is in C1 and capital F has this representation. That means what? F is in C1 means what? It is 1 times continuously differentiable. That means capital F is differentiable and derivative is continuous, and capital F has these many components. That means each of del g del x1, del g del x2, del g del xn, each of them differentiable. That means second order partial derivatives of g will exist, okay, and these are continuous. So, that means in other words g is in C2. Okay. So, that means if capital F is in C1, that means it implies that scalar potential g is in C2. Why? Because of course already, because capital F is equal to grad of g, that means first order partial derivative already exists. Now, I am assuming that given that capital F is in C1, that means all the components, that means partial derivative of g with respect to x1, partial derivative of g with respect to x2 up to partial derivative of g with respect to xn, each of them will be once differentiable again. That means all the second order partial derivative exists and they are continuous. And what does it mean? If all the first order partial derivative, second order partial derivative exist of some scalar potential g, and if they are continuous, that means g is in C2. So, therefore, capital F is in C1 implies g is in C2. So, now since g is in C2, so that means what? That means I can consider the derivative. So, that means what is Fi? So, Fi is this one. Okay. So, that means capital F is in C1 means what? Del g del xi, this is one more differentiable. So, that means I can talk about del Fi del xj, which is nothing but del 2g, what is called del 2g del xj xi. Or you can write it in this way. I think it's better to write del Fi del xj, which is semi del xj of my function del g del xi. Then what is this? This is the notation del 2g del xj del xi. So, that means first you perform the derivative with respect to ith variable and then jth variable. Okay. So, this is I am talking about the derivative, partial derivative of Fi with respect to xj. Now, you can do the partial derivative of fj with respect to xi. So, that means you can have del fj del xi. Okay. And what is del fj? That means this is nothing but del xi of del g del xj. And what is this? This is del 2g del xi del xj. Okay. So, therefore, I have dj dig and di djg, but what is small g? Small g is C2. That means all the second order partial derivative exists and they are continuous. Now, if you remember, if I have a function scalar potential g, suppose all the second order partial derivative exists and continuous, then the mixed derivatives will exist and they are equal. Na? So, therefore, dj dig, which is same as di djg, because of g is in C2, because of small g is in C2. And once this is the fact, then what is this? dj dig, which is nothing but dj fi, and di djg means what? Di djg means di fj. So, therefore, dj fi, which is same as di fj, and which is nothing but the conclusion. Clear? So, important part is that, so assume that it is conservative vector field. then by the earlier theorem it is a gradient vector field. So, that means you have a scalar potential small g such that capital F is exactly equal to gradient of g. Now, capital F is a C1 vector field, and which implies that your scalar potential small g is in C2. That means all the second order partial derivative exists and they are continuous, and hence the mixed derivative, that means if I perform the partial derivative of g with respect to say xi variable first and then xj, or xj variable first or xi, does not matter, both are same. So, these are same, and that dj di and di dj same implies that corresponding dj fi di fj same, because this is the corresponding equation. Okay. So, that is nothing but the necessary conditions. So, if I have a conservative field, if I have a component functions of capital F is small f1, small f2 up to small fn, you take two component functions small fi and small j where I not equal to j, then if I perform the partial derivative of fi with respect to xj variable, which is same as partial derivative of fj with respect to xi variable at any point. So, that is necessary conditions. Okay. So, but this necessary conditions, so necessary conditions for conservativeness are not sufficient conditions to ensure the conservativeness. So, therefore, you can say that, well, if I have a conservative vector field, then it will have this kind of conditions. Now, will that condition be sufficient? Answer is no. So, these are the example. What is the example? So, this example, first example, capital Fy, capital F at the point xy. I think this vector field you already have seen in my last couple of slides. Minus y I cap plus x j cap divided by x square plus y square, but now the look at the domain, domain is punctured plane. So, that means I am taking about the origin from R2. Now, this is not a conservative vector field in D star. Okay. Now, if you remember, I have calculated this vector line integral C capital F dr, where I think C is a circle with unit radius, and it turns out I think it is pi. If I go back, I think you will see. Let me just go back, I think I have calculated it, right. Yeah, look. So, this is my vector field capital F with my domain D star, and I am taking a circle, okay, centered at origin with radius 1, and what it turns out that integration over C f dr, which is actually 2 pi, which is non-zero. So, therefore, it is not a conservative vector field. Okay. For a conservative vector field, I need it has to be 0. Okay. So, therefore, it is not 0. So, therefore, it is not conservative. Okay. So, it is not a conservative vector field. But what is my capital F, which is I can write it as capital M xy I cap plus capital N xy j cap. What is my capital M? Capital M is equal to minus y divided by x square plus y square, and capital N is equal to x by x square plus y square. And you just observe by looking at the functions capital M and capital N that the capital, if I take the, well, if I take the partial derivative of capital N with respect to x variable, which is same as partial derivative of capital M with respect to n variable. So, because what is the components? Capital F has two components, capital M and capital N, right. You can write it as F1, F2. Okay. So, therefore, if I perform the partial derivative of F1 with respect to x2 variable, that means if I perform the partial derivative of capital M with respect to y variable, right, you just relate it. So, capital F you can have it say F1, F2, and which is same as capital M, capital N. So, what the theorem says, that means del F1 del x2, suppose if I have the variable x1 comma x2, right. So, that is same as del f2 del x1. So, this actually boils down to what is my f1 m. So, that means del m, and what is my x2. So, x1 is x, x2 is y. So, therefore, this is del y, which should be del n, f2 is n, and del x1 is del x. That means this condition one needs to verify whether this is true or not. By looking at the functions capital M and capital N, you can easily calculate that del n del x is exactly equal to del m del y in the domain D stars. So, therefore, it satisfies my conditions, this earlier condition, necessary conditions, right. But however, my field is not a conservative vector field. So, therefore, this is not a what is called sufficient conditions. Okay. So, now let capital F, okay. So, that is a very nice observation. So, this is the corresponding vector field with this domain. However, if I consider the same vector field, but now here I am actually changing my domain. What is my domain? My domain is collection of all those points x y in R2 where x is positive. That means what? That means x is positive means this is the domain I am talking about. This is a very nice domain actually. This is not a good domain. So, if I have this domain, it says that capital F is a gradient vector field. Now, if I have a gradient vector field, it is a conservative vector field, right. So, that means in other words, capital F you can write it as grad of small f, that means some scalar potential, and what is my scalar potential? F of x y is equal to tan inverse y by x. So, therefore, in this domain my vector field capital F is a gradient vector field and hence it is a conservative vector field. However, if I consider the vector field F with this domain, it is not a conservative vector field, but still it satisfies some necessary condition. I said if I have a conservative vector field, it will satisfy something. That means this is the condition it satisfying. If I combine all those information, it says that whether or not capital F is gradient or conservative field depends on its domain. So, that is very important. So, that means if I change the domain, field becomes conservative or may not be conservative. So, for example, this domain it is not conservative, but if I change the domain, it is actually conservative field. Okay. So, now you can say that okay, can I have some sufficient conditions for this what is called conservativeness. So, necessary conditions I know, and then I say that okay, with that necessary conditions may not be sufficient because two examples I have discussed, because it depends on domain. So, therefore, the question is sufficient conditions for conservativeness on simply connected convex domain. That means, if I have some conditions on the domain, then can I say that the necessary conditions whatever I have achieved, it will become sufficient. So, that is what it is. So, let me just have some definition first. So, let D be a connected set in R2. Connected set I have discussed at the very first couple of lectures I have discussed. So, let D be a connected set in R2. We say that D is simply connected or one connected if every simple closed piecewise smooth curve C lying entirely in D encloses only points of D. So, that is the interior bounded domain to the curve C lies entirely inside D. So, therefore, if I have a domain D, okay, so it says that it is simply connected. Yes, because if I take every simple closed piecewise smooth curve, that means if I take this kind of curve, okay, so this is my domain D. So, it says that okay, lying entirely, of course, it is lying entirely in D, encloses only points of D. So, that means what is the point encloses by this smooth curve? These are the points now, and this is fully inside D. So, therefore, this kind of domain is called simply connected or one connected. So, suppose you have a connected set, you start with a connected set, we say that it is simply connected or one connected. If I take every simple closed piecewise smooth curve, simple closed piecewise smooth curve lying entirely in D encloses only points of D, that means there should not be any interior point which is not a point of D, it should not be the case. Okay. That means whatever simple closed piecewise smooth curve I can take inside D, it encloses only points of D. If this is the case, or in other words you can say that the interior bounded domain, so this is the domain, right, interior domain covered by your what is called simple closed piecewise smooth curve C, that should lies entirely inside D, and this is the domain which is inside D. So, this kind of domain it's called what is called simply connected or one connected. Now, look at the theorem. It says that sufficient conditions for conservativeness in R2. If I start with a domain, not arbitrary domain, if I start with a domain which is simply connected and convex domain. So, two things if I have. If I have a domain which is simply connected and convex, on top of that, if the component functions f1 and f2 satisfies this one, del f1 del x2 is exactly equal to del f2 del x1 at all points of D, then f is actually conservative vector field in D. So, therefore, the necessary conditions become sufficient. So, now I had, that means what? That means I had to restrict my domain D. So, that means it will not, of course, in my last slide you see that if I change the domain, conservativeness fails. Okay, in some domain your field vector field becomes conservative, in some domain it is not. So, this is a sufficient conditions. If I deal with D which is simply connected and convex domain in R2, and suppose since I am in R2 to R2 vector field, and suppose you have component functions say f1 small f1 and small f2, and if it satisfies that f1 partial derivative of f1 with respect to x2 which is same as partial derivative of f2 with respect to x1, then the f is conservative, that means f is capital F is a gradient vector field. Okay. Okay, so one example. So, example finding scalar potential. Okay, I think this partial differential equation you have to solve. So, I think I have already discussed one example. This is another example. So, again it is a vector field from R2 to R2 capital Fxy, which is exactly equal to 2x minus 3y minus 4 plus 4y minus 3x plus 2, and find the scalar potential. What you have to do? You have to just solve the partial differential. That means dy by dx is exactly equal to this by this. Then you just solve it, then you will have. So, I have written the answer, you just calculate it, you just solve the differential equations, then I think you will be able to show that the corresponding scalar potential f is nothing but these functions. Okay. Okay, so I think I should stop here. Equivalent. So in my next class, I will talk about what is called I can visualize my vector field in equipotential. What is called, that's the written equipotential curves. Okay, so I have talked about arrows. I have talked about integral curves. Now I want to visualize my vector fields in terms of equipotential curves. So I think that concept I will talk about in my next lecture. Okay, so up to that part is okay. So therefore I have what I have. So I have a conservative vector field. I have a gradient vector field. I have a path independence vector field. Right, everything becomes equivalent. And then I talked about that. Okay, if I have a gradient vector field, I have a necessary conditions, right? And then I talked about, okay, whether that necessary condition, whether it is sufficient or not. Then I two examples I have discussed. Yes, it somehow it is the necessary condition, it's not a sufficient one. That means I need some extra conditions. And what extra condition, what sort of extra conditions I need? Then I say that, okay, you have to deal, or you have to start with a vector field with nice domain. Nice domain means your domain should be simply connected or path connected. So if I start with a very nice simply connected or one connected and convex domain, then along with that, okay, if I have a component functions f1, f2, and if they satisfy this kind of conditions, del f1, del x2 is exactly equal to del f2, del x1, that means this is the one, so sufficient condition for conservativeness, then my vector field capital F is a conservative vector field. That means it is a what is called gradient vector field. Okay, so up to that part it's perfectly all right. And one example I say that, okay, capital F is there, then what is the corresponding scalar potential? You can just solve the differential equations. I already discussed in my last lecture how to, given a what is called vector field capital F, how do I get the scalar potential? That means you have to just solve the what is called partial differential equations, and I have already given the answers F. If you do that, then this is the corresponding answers. Okay, so I think I should stop here. So this is all about what is called gradient vector field, conservative vector field, and path independence vector field. Now, as I said, next lecture I will talk about what is called equipotential curve. Okay, so how I visualize my vector field in terms of equipotential curve. In terms of arrows and integral curves, I already discussed. Now I will talk about what is called in terms of equipotential curves, and then I will talk about what is called divergence, curl, and Laplace operator. Okay, so I think I should stop here. Thank you.